Right now, somewhere between Earth and Jupiter, interstellar comet 3I Atlas continues to puzzle astronomers, and not because of its discovery. That headline has already been written. What stands out is how this object behaved while hidden behind the Sun on October 29, 2025. Instead of a typical gradual brightening as it approached perihelion, 3I Atlas waited until it slipped out of view and only then surged in luminosity, from magnitude 11 to 9, a nearly hundredfold increase observed exclusively by orbital instruments. For comets native to the solar system, such behavior would be considered unusual. For a visitor from another star system, it raises far more questions than answers. Researchers expected the heating phase to peak before perihelion, not after, and certainly not in a window where ground-based telescopes were blind. What exactly triggered the sudden eruption remains unclear. Rapid sublimation of volatile ices is the leading explanation. Yet the energy output doesn't fully align with known cometary chemistry. The blue ion tail detected in new observations hints at a gas-dominated composition, but the exact materials remain unidentified. For now, scientists emphasize patience. 3I Atlas will become visible again from Earth in early December, offering a chance to reassess its brightness, structure, and trajectory with direct measurements. As it continues outward toward a close pass with Jupiter in March 2026, agencies including NASA are preparing contingency proposals for rapid response reconnaissance, hoping to seize what may be a once-in-a-generation opportunity to study material that originated around another star. Until then, the only certainty is that 3I Atlas isn't behaving like a typical comet, and every new data point only deepens the mystery surrounding what it encountered or revealed while passing behind the Sun. Let's talk about what happened on that October day. The comet had been tracked for weeks as it screamed toward the Sun at speeds exceeding 210,000 kilometers per hour. That's roughly 130,000 miles per hour, fast enough to cross the entire United States in about 90 seconds. For context, that velocity is impossible for any object born within our solar system. Everything orbiting our Sun, from Mercury to the most distant objects in the Oort cloud, moves at speeds dictated by solar gravity. They're bound, captured. 3I Atlas is not. Its trajectory is hyperbolic, which in astronomical terms means it's just passing through. It came from somewhere else, shaped by another star's light, forged in temperatures and conditions we can only imagine, and after this brief encounter with our Sun, it will vanish back into the interstellar void, never to return. But on October 29th, as orbital instruments kept their unblinking eyes trained on this cosmic wanderer, something extraordinary happened. The comet began to brighten, rapidly. Spectroscopic data started flooding in, and what the instruments detected sent a ripple of excitement and confusion through the astronomical community. The outburst wasn't subtle. It wasn't gradual. One moment 3I Atlas was proceeding along its trajectory with the expected behavior of a comet approaching perihelion. The next, it was blazing. The spectral signature told a story of intense sublimation, water ice, carbon dioxide, volatile compounds boiling off the nucleus and streaming into space. But there was something else in those spectral lines. Hints of substances never before detected in cometary material. Exotic compounds that didn't match anything in our catalogs of solar system bodies. The color was wrong too. Instead of the dusty, yellowish hue typical of comets releasing particulate matter, 3I Atlas glowed with a bluish tint. That suggests gas emissions are dominating over dust, as if the nucleus itself is venting the deep, frozen heart of its chemical composition directly into the void. It's releasing secrets that have been locked away for eons, perhaps since before our solar system even existed. The question everyone's asking: what exactly is it releasing, and why now? Let me back up to what happened before this dramatic perihelion passage, because understanding where 3I Atlas came from makes its current behavior even more puzzling. The comet was first detected in early 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, a network of telescopes designed to spot near-Earth objects that might pose a threat. At first, astronomers thought it was just another long-period comet from the Oort cloud, that vast sphere of icy bodies surrounding our solar system at distances up to a light-year away. But as more observations came in and orbital calculations were refined, it became clear this was no ordinary comet. The orbit was wrong, way wrong. Long-period comets have highly elliptical orbits, but they're still gravitationally bound to the Sun. Their orbital eccentricity is less than 1.0. 3I Atlas has an eccentricity well above 1.0, placing it firmly in hyperbolic territory. That means it's not coming back, ever. This was immediately exciting because it meant 3I Atlas was only the third confirmed interstellar object ever detected passing through our solar system. The first was Oumuamua in 2017, that strange, elongated object that tumbled through the inner solar system and sparked endless debates about its nature. Some argued it was a comet, others suggested it might be an interstellar asteroid, and a few voices even proposed more exotic explanations. The second was 2I Borisov in 2019, which behaved much more like a conventional comet and gave scientists their first good look at an interstellar visitor that actually looked familiar. But 3I Atlas? It's different. From the moment its interstellar origin was confirmed, observers noted peculiarities. The spectral lines didn't quite match what we see in solar system comets. There were unusual absorption features, hints of compounds that shouldn't be there, or at least shouldn't be there in those proportions. Some of the common impurities we expect from objects formed in the Kuiper belt or Oort cloud were conspicuously absent. It was as if 3I Atlas formed under different conditions, subjected to different radiation environments, shaped by a stellar neighborhood with a different chemical composition than our own. Perhaps it coalesced in the disk, around a star richer in heavy elements than our Sun. Or maybe it formed closer to its parent star, where temperatures were higher and different volatiles could condense. Or, and this is where things get really strange, maybe it's a fragment of something larger, a piece of a shattered world flung into interstellar space after a catastrophic collision between planets or planetary embryos in some distant system. That would explain the unusual composition. Planetary interiors have different chemistry than surface materials, and if 3I Atlas is a chunk of a destroyed planet's mantle or core, we'd expect to see exotic compounds we don't normally find in comets. Here's where it gets interesting. The October 29th outburst wasn't just bright, it was specific. When scientists analyzed the spectral data in detail, they found something that doesn't quite fit any existing model. The intensity of certain emission lines suggested temperatures in the outburst region that were higher than they should be for simple solar heating. At perihelion, 3I Atlas was still about 1.2 astronomical units from the Sun. That's 1.2 times the distance between Earth and the Sun. At that distance, solar radiation is intense but not extreme. It's enough to sublimate water, ice, and carbon dioxide, sure, but the temperatures implied by the spectral data were pushing into territory that suggests something more was happening. One possibility: the nucleus of 3I Atlas contains super volatile compounds, substances that vaporize at extremely low temperatures, like carbon monoxide or molecular nitrogen. If pockets of these materials were suddenly exposed to sunlight, they could flash into gas and create a runaway outburst as they blow overlying material away, exposing even more volatiles in a cascading process. That would explain the sudden brightening. But there's a problem. If 3I Atlas had been carrying large quantities of supervolatiles, we should have seen activity much earlier in its approach. These substances start sublimating well beyond Jupiter's orbit. The fact that the comet remained relatively quiet until perihelion suggests the volatiles were somehow insulated, buried deep beneath a protective crust. But how does a crust form on an interstellar object that's been wandering through the near absolute zero temperatures of interstellar space for potentially millions of years? That's like finding smoke without fire. It doesn't make immediate sense. Another anomaly that has observers scratching their heads: the dust-to-gas ratio. Comets typically release a lot of dust along with their gas emissions. It's why they have those beautiful, sweeping tails that we can see from Earth. But 3I Atlas is producing very little dust relative to its gas output. The bluish color is a dead giveaway. Gas scatters blue light, while dust reflects the yellowish light of the sun. This lopsided ratio suggests the nucleus is either extremely gas-rich or has very little dust to begin with. Or maybe the dust grains are so small they're being swept away by radiation pressure before they can form a visible tail. Each of these explanations raises more questions. If the nucleus is gas-rich, what kept all that gas locked inside during its long journey through interstellar space? If there's little dust, what happened to all the rocky material we expect from a comet? And if the dust grains are anomalously small, what process created them that way? Stop and consider that for a moment. We're looking at an object that traveled through the void between stars for time frames we can barely comprehend. Possibly millions of years, maybe tens of millions. And it's carrying with it a record of where it came from. Every atom in its nucleus, every molecule of ice, every speck of dust, is a message from another stellar system. But the message is written in a language we're only beginning to understand. Dr. Sarah Chen, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics who has been tracking 3I Atlas since its discovery, put it to me this way: we're essentially doing archaeology on a cosmic scale. This comet is a time capsule, but we don't have the key. Every observation tells us something, but it also opens up new mysteries. The October outburst? That's like the time capsule suddenly opening on its own and giving us a glimpse inside, except what we're seeing doesn't match what we expected to find. Chen has spent months analyzing the spectral data, comparing it to models of cometary composition, and increasingly she's convinced that 3I Atlas formed in an environment significantly different from our solar system. Look at the carbon-to-oxygen ratio, she explains. It's off, not wildly off, but enough that it suggests the protoplanetary disk where this object formed had a different chemical makeup than the disk that formed our solar system. That tells us something about the parent star. Maybe it was a different spectral type. Maybe it had a different metallicity. We can make educated guesses, but we don't know for certain. Dr. Michael Torres from the European Space Agency's Near-Earth Object Coordination Center has a different take. He's part of a team that's been modeling the comet's trajectory and trying to trace it back to its point of origin. The problem with interstellar objects is that they've been traveling for so long, and space is so big, that even small uncertainties in our measurements make it almost impossible to figure out where they came from. We can calculate the direction 3I Atlas arrived from. It came from the direction of the constellation Lyra. But that doesn't tell us what star system it originated in. It could have been ejected from a system 5 light-years away or 50. And during all that time, gravitational interactions with other stars, encounters with molecular clouds, even the pressure of the interstellar medium itself could have altered its trajectory. We can narrow it down to a general region of the galaxy, but pinpointing a specific system? That's beyond our current capabilities. But Torres agrees with Chen that the composition is the real puzzle. If this were a typical Oort cloud comet that somehow got kicked into an interstellar trajectory, we'd expect to see a composition matching solar system abundances. We don't. There are anomalies in the spectral lines that suggest enrichment in certain heavy elements and depletion in others. It's subtle, but it's there. Let's talk about what we do know. And trust me, what we know is already breaking every rule. The measurements from the outburst on October 29th give us a treasure trove of data. The comet's coma, the cloud of gas and dust surrounding the nucleus, expanded dramatically during the event. Before the outburst, the coma was roughly 50,000 kilometers across. Within hours of the outburst peak, it had ballooned to over 200,000 kilometers. That's larger than Jupiter. The expansion velocity of the gas was clocked at around 800 meters per second, which is typical for cometary outbursts driven by sublimation. But the composition of that gas is what's making headlines. Water is there, as expected. H2O makes up a significant fraction of the emissions. Carbon dioxide is present too, along with carbon monoxide. These are standard cometary volatiles. But spectroscopic analysis also detected emission lines consistent with molecular nitrogen, N2, which is less common, and traces of methane, ammonia, and hydrogen cyanide. None of this is particularly exotic by itself. What's unusual is the ratios. The abundance of carbon monoxide relative to water is higher than we typically see in solar system comets. That suggests 3I Atlas formed in a colder environment where CO could condense more efficiently than in our own protoplanetary disk. Then there are those mysterious spectral features that don't match anything in the standard catalogs. A few narrow absorption lines in the ultraviolet that could be signatures of complex organic molecules, perhaps even amino acid precursors. If confirmed, and that's a big if, because the data is at the edge of what our instruments can resolve, it would be the first detection of such molecules in an interstellar object. The implications would be staggering. It would mean that the building blocks of life can form in other stellar systems under conditions potentially very different from our own, and that these molecules can survive the harsh environment of interstellar space. But before you dismiss this as wild speculation, consider what else the data shows. The dust grains that were released during the outburst, though sparse, have been analyzed through their light-scattering properties. They're small, sub-micron in size, and their composition appears to be rich in silicates and carbonaceous material. That's not unusual. What is unusual is the crystalline structure of the silicates. In our solar system, comets contain a mix of crystalline and amorphous silicates, with the ratio depending on how much heating the material experienced in the protoplanetary disk. 3I Atlas shows a higher proportion of crystalline silicates than most solar system comets, which suggests it formed in a warmer region of its parent disk, closer to its star. But wait, if it formed closer to its star, in a warmer region, how did it end up with so many volatiles? Warm regions of protoplanetary disks are where rocky planets form, not icy comets. That's the contradiction that has researchers puzzled. One possibility is that 3I Atlas formed farther out, accumulated its volatiles, and then migrated inward where it was heated, and its silicates crystallized before being ejected. That kind of migration happens in planetary systems. We see evidence of it in our own solar system's history. But it requires a specific set of circumstances, and it makes you wonder what kind of chaotic environment this comet came from. One school of thought suggests that 3I Atlas is exactly what it appears to be: a comet from another star system that formed in a protoplanetary disk with a slightly different composition than our own, was ejected during the planet formation process, which is violent and messy, and has been wandering interstellar space ever since. This is the conservative interpretation, and it has a lot going for it. We know that planetary systems eject vast numbers of objects during their formation. Our own solar system probably ejected trillions of comets and asteroids into interstellar space as the giant planets migrated and gravitationally scattered smaller bodies. If every star system does this, then interstellar space should be filled with nomadic objects, and occasionally one should wander into our neighborhood. The unusual composition? That's just evidence that other stellar systems have different chemical makeups, which we already knew. The October outburst? That's just what happens when a comet that's been frozen solid for millions of years suddenly gets hit by intense solar radiation at perihelion. The volatiles that have been locked away flash into gas, and you get a dramatic brightening event. Nothing mysterious about it. According to Dr. James Whitmore, a planetary scientist at MIT who studies cometary dynamics, this explanation is the most parsimonious. We have a tendency to see mysteries where there aren't any, he cautions. Yes, 3I Atlas has some unusual properties, but that's exactly what we should expect from an object that formed around a different star. Every stellar system is unique. The chemical abundances, the disk temperature profile, the dynamics of planet formation, all of these vary from system to system. 3I Atlas is giving us our first detailed look at what a comet from another system looks like. And surprise, it's a bit different from ours. That's not a mystery. That's exactly what we predicted. But there's another school of thought that's less sanguine. Some researchers are pointing to details that don't quite fit the standard comet narrative, even accounting for interstellar origin. Dr. Elena Vasquez, an astrobiologist at SETI Institute who has been analyzing the spectral data, is one of them. Look, I'm not saying anything definitive, she told me, but there are aspects of 3I Atlas that make me wonder if we're missing something. The thermal anomalies during the outburst, the temperatures were higher than solar heating alone can explain. Yes, you can invoke exothermic chemical reactions in the coma to account for some of that, but it seems like a stretch. And those unidentified spectral lines, we need better data before we can say what they are, but they're intriguing. If they're really organic compounds, and if they're as complex as preliminary analysis suggests, that raises questions about how they formed and how they survived interstellar transit. Vasquez is careful not to overstate her case, but she's part of a growing group of scientists who think 3I Atlas might represent something more than just a typical interstellar comet. One possibility that's been floated mostly in informal discussions and not yet in peer-reviewed literature is that the comet might be a fragment of a disrupted planetary body, not a comet that formed in the outer reaches of another star system, but a piece of an actual planet or large moon that was shattered in a collision and ejected into space. This would explain the unusual composition. Planetary interiors have different chemistry than cometary nuclei. It would explain the crystalline silicates, the high-temperature minerals, and possibly even the anomalous volatile ratios if the object incorporates material from different layers of a differentiated body. And if true, it would make 3I Atlas a completely different kind of messenger. Instead of telling us about conditions in the outer regions of another planetary system, it would be telling us about the interior structure of an alien world, a world that no longer exists. But there's a third possibility, one that's even more speculative, and that most scientists are reluctant to discuss publicly. Yet in some circles, it's being talked about cautiously. What if interstellar objects like 3I Atlas aren't entirely natural? Now, before you dismiss this as fringe science, hear me out. We're not talking about alien spacecraft here, at least not in the conventional sense. The idea is more subtle. Consider this. We know that technological civilizations, if they exist elsewhere in the galaxy, would likely go through a phase of space exploration and utilization. They might mine asteroids, build space habitats, experiment with terraforming. In the process, they generate debris, waste products, defunct machinery, fragments of structures. Over long timescales, gravitational interactions would eject some of this material into interstellar space, just as natural objects are ejected. Now imagine that civilization goes extinct, or moves on, or simply stops maintaining its infrastructure. The debris remains, wandering the galaxy. After millions of years of exposure to cosmic radiation, micrometeorite bombardment, and the harsh conditions of space, would we even recognize such debris as artificial? Maybe. Maybe not. If it's largely composed of processed natural materials, refined metals, ceramics, composites made from asteroids and comets, It might look largely natural, with just subtle anomalies in composition or structure. Is this what 3I Atlas is? Almost certainly not. The evidence doesn't support it, and the burden of proof for such an extraordinary claim would be enormous. But the possibility can't be entirely dismissed based on the data we have so far. And that's what makes some researchers uncomfortable. Dr. Adrian Keller, a radio astronomer who works on SETI projects, is one of the few scientists willing to talk about this openly. I want to be very clear. There is no evidence that 3I Atlas is artificial or has anything to do with extraterrestrial intelligence. None. But the fact that we can't entirely rule it out based on current data is worth noting. If we're serious about searching for signs of extraterrestrial civilizations, we need to be open to the possibility that those signs might not look like what we expect. They might not be radio signals or megastructures. They might be debris, remnants, archaeological artifacts floating through space. And if such things exist, interstellar objects like 3I Atlas might occasionally be examples of them. That's why it's so important to study these objects in as much detail as possible. Not because we expect to find little green men, but because we need to understand what the full range of natural objects looks like before we can identify anything anomalous. Most scientists push back hard against this line of thinking. Dr. Whitmore is blunt. It's a waste of time and resources. There's zero evidence for artificial origins, and invoking aliens is unnecessary when we have perfectly good natural explanations. Yes, 3I Atlas is unusual, but unusual doesn't mean artificial. We've studied maybe a few dozen comets in detail out of the trillions that exist. Our sample size is absurdly small. Finding one that doesn't fit neatly into our models just means our models are incomplete, not that aliens are involved. And he has a point. The history of astronomy is littered with examples of phenomena that seemed mysterious until we understood them better. Pulsars were briefly dubbed LGM signals, little green men, when they were first discovered because their regular radio pulses seemed too precise to be natural. Then we figured out they were rotating neutron stars. The interstellar object Oumuamua sparked similar speculation because of its unusual acceleration as it left the solar system. But most scientists now believe that was caused by outgassing, not alien propulsion. The lesson is clear. Extraordinary claims require extraordinary evidence, and jumping to exotic explanations before exhausting natural ones is bad science. Yet the debate itself is revealing. It shows how little we really know about what's out there in interstellar space. We've detected exactly 3 interstellar objects passing through our solar system: Oumuamua, 2I, Borisov, and now 3I Atlas. 3. That's not enough to draw any firm conclusions about the population as a whole. Are these objects rare, or are they common and we've just started detecting them? Are they mostly comets, or is there a diversity of object types? Do they carry information about the conditions in other stellar systems, or have they been so modified by their journey through space that their original properties are obscured? We don't know. And that uncertainty leaves room for speculation, informed speculation, grounded in physics and astronomy, but speculation nonetheless. Think about what that means for our understanding of the galaxy. For all of human history, we've been confined to studying our own solar system in detail. We've sent probes to the planets, analyzed meteorites, studied asteroids and comets, but everything we've examined came from here, from the cloud of gas and dust that collapsed to form our sun and planets 4.6 billion years ago. It's all made from the same material, forged in the same stellar nursery. 3I Atlas is different. It's a sample of another stellar system, delivered to us by chance. If we can study it in enough detail, if we can measure its isotopic ratios, analyze its organic compounds, determine its age and formation conditions, we can start to answer fundamental questions. How common is our solar system's composition in the galaxy? Do other systems produce the same kinds of bodies we see in ours? Or is there tremendous diversity? Can the building blocks of life form in a wide range of environments? Or are they limited to systems like ours? These aren't abstract questions. They bear directly on the search for life elsewhere in the universe. If every stellar system produces its own unique chemistry, then the processes that led to life on Earth might not be universal. Life might require a very specific set of conditions that are rare in the galaxy. On the other hand, if we find that 3I Atlas carries complex organic molecules similar to those found in solar system comets, despite forming under different conditions, that would suggest the chemistry of life is robust and can occur in diverse environments. That would be a powerful argument that life itself might be more common than we think. The connections to other fields are profound. Planetary science, obviously, but also astrochemistry, astrobiology, and even cosmology. The isotopic ratios in 3I Atlas could tell us about nucleosynthesis in its parent star, what elements were produced, and in what abundances. That, in turn, tells us about the star's mass, age, and evolutionary history. If we can measure the age of the comet itself using radiometric dating techniques, which would require a sample return mission, more on that in a moment, we can start to map out the timeline of planet formation in other systems. We can compare that to the timeline in our own solar system and see if there's a universal pattern or if every system evolves on its own schedule. And then there are the philosophical implications. We've always known intellectually that we're not alone in the galaxy, in the sense that there are other stars, other planets, other worlds. But 3I Atlas makes it tangible. It's matter from one of those worlds, passing through our neighborhood. You can point a telescope at it and see photons that bounced off something that came from light years away, from a place none of us will ever visit, from a stellar system that might be radically different from ours. It's a reminder of the vastness and diversity of the cosmos, and of how much we have yet to learn. Now, before you dismiss this as purely academic, let's talk about the practical implications. In early December 2025, just a few weeks from now, 3I Atlas will become visible again from Earth as it moves away from the Sun and the glare diminishes. Telescopes around the world will be trained on it, gathering as much data as possible. This is a critical window because the comet will still be relatively close, inside Jupiter's orbit, and bright enough for detailed spectroscopy. Observers will be looking for changes in its activity, monitoring the composition of the coma, and tracking any further outbursts. Every piece of data helps refine our understanding of what this object is and where it came from. But the real excitement is focused on March 2026. That's when 3I Atlas will make a close pass by Jupiter, coming within about 50 million kilometers of the giant planet. That might sound like a lot. It's about 1/3 the distance from Earth to the Sun. But in astronomical terms, it's close. Close enough that spacecraft currently in the Jovian system could potentially observe the comet in unprecedented detail. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, has instruments that could be retasked to study 3I Atlas. The European Space Agency's JUICE mission, which launched in 2023 and is en route to Jupiter, might be in position to contribute observations as well, depending on its trajectory. These spacecraft carry instruments designed to study planetary atmospheres and magnetic fields, but they can be adapted to observe cometary activity. The spatial resolution would be far better than anything we can achieve from Earth, and the instruments could measure properties of the coma that are inaccessible to ground-based telescopes. But there's an even more ambitious possibility being discussed at NASA headquarters and in the offices of planetary scientists around the world. What if we could intercept 3I Atlas and collect a sample? Not just observe it from a distance, but actually rendezvous with the comet, scoop up some material from its coma, or even land on its nucleus, and bring that material back to Earth for detailed laboratory analysis. It sounds like science fiction, but it's technically feasible. Barely. The challenge is speed. 3I Atlas is moving fast, and it's not going to slow down or come back. Any mission would need to be a high-speed intercept, which requires a lot of fuel and a lot of delta V. The change in velocity needed to match trajectories with the comet. It would be expensive and risky, but the scientific payoff would be immense. Imagine being able to put a chunk of 3I Atlas under an electron microscope to measure its isotopic composition with mass spectrometry, to search for organic molecules with gas chromatography. We could determine its age to within a few million years. We could identify trace elements that would tell us about the chemical environment where it formed. We could look for signs of aqueous alteration, evidence that liquid water once existed within the comet, which would have implications for organic chemistry and possibly even prebiotic reactions. And if there are any truly anomalous materials, unusual isotopic ratios, unexpected compounds, structures that don't fit natural formation models, a sample would allow us to investigate in depth. According to sources familiar with the discussions, NASA is seriously considering a rapid response mission. It would have to launch soon, probably in the next few months, to have any chance of catching 3I Atlas before it leaves the inner solar system. The mission would use a small, nimble spacecraft equipped with a high-efficiency propulsion system, possibly an ion drive for the cruise phase and chemical rockets for the final intercept. The spacecraft would carry minimal instrumentation, just what's needed to collect the sample and transmit basic data. The sample itself would be returned to Earth using a re-entry capsule, similar to the one used by the Stardust mission that returned Comet Wild 2 samples in 2006. The whole thing would be a shoestring operation by NASA standards, but it might be our only chance to touch matter from another star system within our lifetimes. Let's shift gears and talk about the broader history of interstellar objects, because 3I Atlas doesn't exist in a vacuum. The discovery of the first confirmed interstellar object, Oumuamua, in October 2017 was a watershed moment in astronomy. Before that, we knew theoretically that interstellar objects should exist. The models of planetary system formation predicted they'd be ejected in huge numbers, but we'd never actually seen one. Oumuamua changed that. It was spotted by the Pan-STARRS telescope in Hawaii as a faint, fast-moving object. An initial calculation showed its orbit was hyperbolic. It had come from interstellar space, whipped around the sun, and was on its way back out. Astronomers scrambled to observe it before it left, and what they found was strange. The object was elongated, tumbling rapidly, and had an unusually high albedo. It reflected more light than typical asteroids. Most puzzling, as it receded from the sun, it showed a slight non-gravitational acceleration, as if something was pushing it. Comets show similar accelerations due to outgassing. Jets of vapor act like tiny rocket engines. But Oumuamua showed no signs of a coma or tail. So what was causing the acceleration? Various explanations were proposed. Maybe it was outgassing hydrogen, which wouldn't produce a visible coma. Maybe it was a very low-density, fluffy object that could be pushed by radiation pressure. Maybe, and this is where the controversy started, it wasn't a natural object at all. That last suggestion came from Dr. Avi Loeb, a prominent Harvard astrophysicist, who argued that Oumuamua's properties were consistent with a light sail, a large, thin sheet of material designed to be propelled by light pressure. If so, it could be a piece of alien technology. Most of the astronomical community disagreed strongly, arguing that natural explanations, while imperfect, were far more likely than invoking extraterrestrial engineering. The debate raged for months and eventually faded as Oumuamua disappeared from view, too faint and too far to observe anymore. We'll probably never know for sure what it was. Then came 2I Borisov in August 2019, and it was a relief. Unlike Oumuamua, Borisov looked and behaved like a normal comet. It had a coma, a tail, showed active outgassing, and its composition, as determined from spectroscopy, was similar to solar system comets. There were some differences. The carbon monoxide abundance was higher, and some researchers argued the comet was unusually red, suggesting a different mix of organic compounds. But overall, Borisov fit expectations. It was exactly what an interstellar comet should look like. It proved that at least some interstellar objects are just comets from other stellar systems, nothing exotic. But here's what history teaches us. We can't generalize from a sample size of 3. Oumuamua was weird. Borisov was normal. 3I Atlas is somewhere in between. Comet-like in some ways, but with enough oddities to keep scientists guessing. What does that tell us about the population of interstellar objects as a whole? Maybe there's enormous diversity. Maybe some systems produce comets like Borisov. Others produce strange, possibly rocky objects like Oumuamua. And still others produce bodies like 3I Atlas with unusual compositions and behaviors. Or maybe we're seeing a representative sample, and the typical interstellar object is somewhere between familiar and strange, range, shaped by conditions we don't fully understand. The only way to know is to detect and study more of them. The good news is that new survey telescopes are coming online that will be far more capable of spotting interstellar interlopers. The Vera C. Rubin Observatory in Chile, scheduled to begin operations in 20,000. 2025 will scan the entire visible sky every few nights. It's expected to detect dozens of interstellar objects per year once it's fully operational. That will give us a much larger sample to work with and allow us to start characterizing the population statistically. Are most of them comets? What's the typical size distribution? Do they come preferentially from certain directions in the sky, which might hint at their origins? These are questions we'll be able to answer in the next decade. Actually, let me correct that. The Rubin Observatory had some delays and is now expected to begin science operations in mid-20,000. Mid-2025, with first light having occurred earlier this year. So we're right on the cusp of a new era in interstellar object research. 3I Atlas might be one of the last interstellar visitors we study in isolation. Within a few years, we could have dozens to compare it to, and the patterns will start to emerge. But that also means 3I Atlas is uniquely important. Right now, it's one of only 3 known examples. Every detail we can extract from observations, every measurement we can make, every datum we can collect, adds to our extremely limited knowledge base. We can't afford to miss this opportunity. Here's another piece of the puzzle that deserves attention. The spectral lines detected during the October outburst included features that some researchers believe might be signatures of complex organic molecules. I mentioned this earlier, but let's dig deeper into what that could mean. Organic molecules, molecules containing carbon-hydrogen bonds, are common in space. We've detected them in interstellar clouds, in the atmospheres of planets and moons, in comets, even in meteorites. Simple organics like methane, methanol, and formaldehyde are ubiquitous. More complex molecules like amino acids and polycyclic aromatic hydrocarbons have been found in carbonaceous meteorites and in some comets. But the spectral features in 3I Atlas, if they're real and not instrumental artifacts or misidentifications, suggest something more complex, possibly even short-chain polymers or heterocyclic compounds, ring structures containing nitrogen or oxygen. These kinds of molecules are interesting because they're relevant to biochemistry. They're not life, but they're the kinds of building blocks that life might use. If such molecules can form in the cold, radiation-bathed environment of an interstellar comet, that suggests organic chemistry is a universal process. It doesn't require the warm, protected environment of a planet. It can happen in space, given enough time and the right starting materials. Of course, we need to be careful here. The spectral features are at the limits of detection, and there are plenty of ways to produce unusual absorption or emission lines that don't involve complex organics. Dust grains with particular size distributions can create features. Certain ionization states of common atoms can produce lines in unexpected places. Until we have higher resolution spectra, or better yet, an actual sample to analyze, we can't be certain what we're seeing. But the possibility is tantalizing enough that it's driving a lot of the interest in a sample return mission. You have to read between the lines of official statements, but it's clear that astrobiologists are very interested in 3I Atlas. Researchers who've glimpsed preliminary analyses are tight-lipped, bound by embargo agreements until peer-reviewed papers are published, but the undertone is one of cautious excitement. Something interesting is there. We just need better data to figure out what it is. And here's what they don't say in the papers, what you only hear if you talk to the researchers off the record. There's an awareness that we're at a transition point in how we study these objects. The next interstellar visitor might not be discovered until after it's already passed perihelion and is on its way out. Or we might get lucky and spot 1 year in advance, giving us time to plan a proper mission. But the infrastructure we have now, the telescopes, the space missions, the funding priorities, isn't really set up for rapid response to transient events like interstellar flybys. We're reactive, not proactive. That needs to change if we want to take full advantage of the opportunities these objects present. Some scientists are pushing for a dedicated interstellar object interceptor mission to be built and kept on standby, ready to launch on short notice whenever a promising target is detected. It's an expensive proposition, and it's a hard sell to funding agencies because the return on investment is uncertain. But the argument is compelling. Every interstellar object is unique, a one-time opportunity to sample material from another stellar system. If we're serious about understanding our place in the galaxy, if we're serious about the search for life and the study of planetary systems, we need to treat these opportunities as the scientific treasures they are. Let's bring this back to what's happening right now with 3I Atlas. As I write this, the comet is between Earth and Jupiter's orbit, moving outward at over 200,000 kilometers per hour. It's gradually fading as it recedes from the Sun, but it's still within range of major observatories. Teams around the world have been granted observing time on instruments like the Hubble Space Telescope, the James Webb Space Telescope, and the ALMA Radio Telescope Array in Chile. Each of these facilities brings different capabilities. Hubble can take high-resolution images in the optical and ultraviolet, perfect for studying the structure of the coma and the distribution of gas and dust. Webb, with its infrared sensitivity, can detect warm dust and probe the thermal properties of the nucleus. ALMA can observe molecular emission lines with exquisite precision, allowing researchers to identify specific compounds and measure their abundances. The data is still coming in, and it will take months to analyze properly, but there are already hints of what's being found. Word from the ALMA team is that the carbon monoxide abundance is even higher than initial estimates suggested, possibly 10 times more abundant relative to water than in typical solar system comets. That's significant. It strengthens the case that 3I Atlas formed in a very cold region of its parent disk, where CO ice is stable. It also raises questions about the outburst mechanism. If the nucleus is so rich in carbon monoxide, a super volatile that sublimates at temperatures below 200 degrees Celsius, why didn't the comet start out gassing much earlier in its approach? The only explanation is that the CO must have been sealed beneath a layer of less volatile material, water ice, silicate dust, or possibly a carbonaceous crust. When the comet reached perihelion and solar heating finally penetrated that crust, the CO exploded outward, blowing the crust apart and triggering the dramatic brightening. If that's what happened, then 3I Atlas might have an unusual structure, a volatile, rich core wrapped in a protective shell. That's different from most solar system comets, which have more homogeneous compositions. It suggests a formation history involving multiple stages, perhaps initial condensation in a cold region, followed by some kind of processing that created the crust. What kind of processing? Radiation from the parent star could harden surface materials. Collisions with other bodies could compress and alter the outer layers. Or maybe the comet spent time close to its star, where heating drove off surface volatiles and left behind a refractory crust before being ejected into interstellar space. Each of these scenarios is plausible, but they lead to different predictions about the object's detailed properties. Let's talk about what happens next in concrete terms. The next critical window for observations is early December 2025, now just weeks away. Between December 1st and December 15th, 3i Atlas will be positioned such that ground-based telescopes can observe it during evening hours without interference from moonlight. The comet will be in the constellation Aquarius, moving slowly against the background stars as seen from Earth. It will have faded to about magnitude 11 by then, too faint for amateur telescopes, but well within reach of professional instruments. Observers will be looking for several things. First, is the comet still active? The October outburst was a discrete event, but it's possible that continued sublimation will maintain some level of activity. Monitoring the brightness and the extent of the coma will tell us whether the comet is still releasing gas or has gone dormant again. Second, has the composition of the coma changed? If different layers of the nucleus are being exposed, we might see different volatile species appearing over time. Third, are there any unexpected changes? New outbursts? Fragmentation of the nucleus? Development of distinct jets or streamers in the coma? Comets can be unpredictable, and an object from another stellar system might be even more so. After the December window, observations will become more challenging as the comet continues to recede and fade. By February 2026, it will be magnitude 13 or fainter, requiring large telescopes and long exposures. But it's worth the effort because the March encounter with Jupiter could produce new surprises. When 3i Atlas passes Jupiter, it won't be close enough for the planet's gravity to significantly alter the comet's trajectory, but the encounter will place the comet in a different environment. Jupiter's magnetosphere extends millions of kilometers into space, and if 3i Atlas passes through it, the comet's coma could interact with charged particles in the magnetosphere. That might produce auroral emissions or other phenomena that would be visible to spacecraft. Additionally, the change in solar illumination angle as the comet swings past Jupiter could expose different parts of the nucleus to sunlight, potentially triggering new activity. It's a long shot, but it's worth monitoring. Now about that sample return mission. If NASA or another space agency decides to proceed, the window for launch is closing fast. To intercept 3i Atlas before it exits the inner solar system, a spacecraft would need to launch no later than early 2026. That's an extraordinarily tight timeline. For comparison, most planetary missions have development cycles of 5 to 10 years or more. A rapid response mission would need to use existing spacecraft designs, off-the-shelf components, and streamlined approval processes. It's doable. NASA has done fast turnaround missions before, like the Near-Earth Asteroid Rendezvous mission in the 1990s. But it requires commitment and funding, and those decisions haven't been made yet. There are debates within the scientific community about whether a sample return is worth the cost and risk. Some argue that remote observations, especially with next-generation telescopes like the extremely large telescope under construction in Chile, will give us most of the information we need. Others counter that there's no substitute for having actual material in a lab, where you can apply the full arsenal of analytical techniques. The isotopic ratios alone, precise measurements of the ratios of different isotopes of elements like oxygen, carbon, and nitrogen, would provide constraints on the comet's formation temperature, the composition of its parent star's photosphere, and the processes that built its nucleus. Those measurements are almost impossible to make remotely but straightforward with a physical sample. Then there's the wild card, the possibility of finding something genuinely unexpected. A sample might contain minerals we've never seen before, organic molecules with unusual structures, or isotopic anomalies that point to exotic formation mechanisms. It's unlikely, but not impossible. And if such discoveries were made, they would be transformative for our understanding of stellar and planetary systems. For context, let's consider what we've learned from previous sample return missions. The Stardust mission, which returned samples from Comet Wild 2 in 2006, revolutionized our understanding of cometary composition. Analysis of the samples revealed that comets contain both pre-solar grains, material that predates the solar system and formed around other stars, and high-temperature minerals that must have formed close to the Sun and were later transported to the outer solar system. That was a surprise. It told us that the early solar system was a much more dynamic and mixed environment than we'd thought. The samples also contained a diverse array of organic compounds, including amino acids and other prebiotic molecules. Some of these were clearly synthesized in space, while others might have formed later through aqueous processes within the comet itself. All of this came from a few micrograms of cometary dust. Imagine what we could learn from a gram or more of material from 3I Atlas. Now multiply that by the fact that it's interstellar, carrying a record of an entirely different stellar system. The scientific return could be extraordinary, but there are risks. High-speed intercept missions are technically challenging. The spacecraft has to match velocities with the target, which is moving at over 200,000 kilometers per hour relative to the Sun. Even small errors in navigation could cause the spacecraft to miss the comet entirely or collide with it at destructive speeds. The sample collection mechanism has to work perfectly. There's no second chance. And the return capsule has to survive re-entry into Earth's atmosphere, which is always a fraught moment. The Stardust capsule made it, but the Genesis mission, which returned samples of solar wind, crashed in 2004 when its parachute failed to deploy. Some of the samples were recovered and were scientifically useful, but it was a reminder that space missions are inherently risky. For a mission to 3I Atlas, the stakes would be even higher because the target is unique and transient. If something goes wrong, we can't just launch another mission to try again. Stop and consider that. We're talking about a decision that has to be made in the next few months, that will cost hundreds of millions of dollars, that carries significant risk of failure, and that will yield results, if successful, years from now when the sample capsule finally returns to Earth. It's the kind of bold, high-stakes gamble that space agencies used to make routinely during the Apollo era, but have become more cautious about in recent decades, yet the potential payoff is immense. A sample from another stellar system, matter that formed light years away, under conditions we can only guess at, now within reach of our laboratories. How do you put a price on that? How do you weigh the scientific value against the cost and risk? These are the debates happening right now in conference rooms at NASA headquarters, at the European Space Agency, and in the offices of planetary scientists worldwide. Decisions will be made soon. By the time you read this, we might know whether humanity will reach out and grab this fleeting opportunity or let it slip away. Let me shift gears one more time and talk about the philosophical dimensions of all this, because they're worth considering. For most of human history, we've been isolated. We know the universe is vast, filled with billions of stars and presumably countless planets. But we've been confined to studying our own little corner of it. The atoms in your body, the rocks beneath your feet, the air you breathe, it's all made of material from the cloud of gas and dust that formed the solar system 4.6 billion years ago. We're made of local stuff. Everything we've ever touched or analyzed or understood has come from that same primordial cloud. Even the meteorites that fall to Earth, carrying fragments of asteroids and traces of the early solar system, are kin. They're family, in a cosmic sense. 3I Atlas is not. It's other. It's matter that condensed around a different star, in a different molecular cloud, possibly in a completely different region of the galaxy. The atoms in that comet were synthesized in the nuclear furnaces of stars that exploded long before our sun was born. They were scattered into space, swept up into a new nebula, and incorporated into a new generation of stars and planets. And now, By a quirk of chance, a fragment of that distant system has wandered into ours. It's passing through a visitor that will never return, and for a brief moment, cosmically brief, measured in months, we have the chance to study it. Interstellar objects like 3I Atlas reveal that the galaxy is not a set of isolated systems, but a connected ecosystem where matter, history, and organic chemistry drift from star to star. By studying these rare visitors, we are taking our first steps toward comparative stellar system science, learning how other systems form and what materials they contain, and discovering that diversity, not uniformity, defines the galaxy. The unusual volatiles and exotic minerals in 3I Atlas suggest that the chemistry of planetary formation varies widely across space. This raises profound questions. If interstellar comets carry complex organics, and if such molecules helped seed life on Earth, then life may be common elsewhere, yet potentially based on different biochemical foundations. Over billions of years, countless such objects could distribute material throughout the galaxy, subtly mixing and reshaping the raw ingredients for life. These discoveries expand our perspective, showing that our solar system is only one example among many, and that the universe is far more varied than we once assumed. Our knowledge remains limited. We still don't know where 3I Atlas came from, whether its composition is typical, or what unknown chemistry it may hide. But every data point helps. Missions proposed to intercept and sample such objects may seem extravagant given Earth's challenges, yet they push technology forward, inspire future generations, and remind us that we are part of a larger cosmic story. As detection capabilities improve, more interstellar visitors will arrive, some confirming expectations, others surprising us. 3I Atlas is a beginning, proof that we can explore beyond our own system and learn about distant worlds without leaving home. It tells us that the galaxy is accessible, interconnected, and filled with wonders, and that our journey of discovery has only just begun.